For the purpose of performing multivariate exploratory data analysis, we have developed a technique that we call adaptable radial axis plots. Radial axis plots are visualization techniques that show multidimensional data samples as points and variables as vectors that represent radial axes. The locations of samples depend on their attributes and on the axis vectors. Their orientation determines the direction in which a variable increases, and the length specifies its influence in the visualization. We have developed a prototype tool that allows to interact with these techniques in several ways. For example, when using the well-known method star coordinates, users can modify the axis vectors in order to search for cluster structure, outliers, or data with special characteristics. In this example, the data are breakfast cereals, and in the final plot, healthier ones are located towards the left. Another well-known method is the principal component biplot, where labeled axes are included in the plots. Users can visually estimate attribute values of samples by orthogonally projecting points onto the axis. Principal component biplots define specific fixed sets of axis vectors that yield optimal estimates in a least square sense for an entire dataset. Therefore, users cannot update the axis vectors freely. We propose using a hybrid strategy where users are able to modify the axis vectors and estimate attribute values optimally. If we use biplot axes in star coordinates, the estimates turn out to be poor, since the differences between the true values and the estimates are usually large. Our technique will be able to find better locations for the two-dimensional points that represent data samples, which will yield smaller estimation errors. For example, this is a star coordinates plot of 5 breakfast cereal variables. The values for protein content are between 1 and 6. Thus, ideally, the point should lie in the shaded region, but many fall outside. Our method will be able to plot the points to different locations, improving the accuracy of the estimates. We can observe the overall accuracy of the estimates by analyzing the sum of estimation errors over every data sample. In this example that uses 4 breakfast cereal data variables, the sum of estimation errors for our method is about 132. These increase up to about 547 when we apply star coordinates. Another way to enhance the estimates consists of applying an orthonormalization procedure on the axis vectors, which leads to an orthographic star coordinates plot. Note that the error drops back to 132. The drawback of this approach is that the new transformed axis vectors may not reflect the user's initial intentions. In some cases, the changes in the axis vectors can be considerable. The goal of our technique is to reduce several estimation errors. Mathematically, we need to consider a vector of differences between the true values and the estimates, and then minimize its norm. We have considered the 3 most common vector norms, which measure the sum of absolute values, the sum of squared values, and the maximum absolute value. Thus, our technique can be defined as a norm minimization problem. This plot uses the L2 norm in order to visualize the breakfast cereal dataset. The L-infinity norm produces a different plot, and the L1 norm provides yet another view of the data. Note that analysts may make different decisions when searching for cereals with large values of protein. In this example, the data is related to cars. Assume we are interested in heavy cars with large acceleration and horsepower, but low fuel consumption. The choice of norm may affect our decisions considerably. The marked red sample does not stand out when using the L2 norm. However, it is an interesting candidate when using the L-infinity norm. Lastly, it would be discarded when applying the L1 norm. Using different norms can therefore be useful for exploratory data analysis, since they may reveal interesting or unexpected features in the data. Finally, the marked sample contains the largest value of acceleration. We can see this by coloring the samples and also by ordering the data. One way to order the data consists of forcing exact estimates on one of the axes. This can be accomplished by introducing a constraint in the convex optimization problem. Here we obtain exact estimates of protein in the example that uses 5 attributes of breakfast cereals. Observe that the approach can be used with any vector norm. A milder constraint consists of forcing the estimates to be ordered correctly on one of the axes. This allows to increase the overall estimation accuracy with respect to the plots based on exact estimates. It is also possible to approximately order the data by enlarging an axis vector. However, this compresses the points and the labels in the direction of the axis. In practice, the axis vector needs to be very large in order to order the data correctly. The resulting plots are very compressed even if we zoom in. A more efficient idea consists of introducing weights in the optimization problem's objective function. These weights control the relative accuracy of the estimates on the axis. In the example, the weight associated with protein is 10 times larger than the rest. The optimization problem focuses on reducing the estimation errors on that axis, which ends up ordering the data. We hope these examples illustrate the benefits of our approach for data analysis.